U.S. semiconductor production investments. The United States is currently engaged in the most ambitious industrial policy mobilization since the mid-20th century, a multi-front campaign to fundamentally restructure the global semiconductor supply chain. This effort, crystallized by the bipartisan CHIPS and Science Act of 2022, is not merely a funding mechanism, but a strategic realignment of national priorities involving national security, economic resilience, and technological sovereignty. The landscape of American manufacturing is being physically altered by capital expenditures exceeding $300 billion, driven by a convergence of federal incentives, geopolitical anxiety regarding East Asian supply concentrations, and the physical limits of Moore's Law that necessitate novel manufacturing paradigms. The scope of this reindustrialization is exhaustive, covering the entire spectrum of semiconductor utility. At one end of the spectrum lies the race for angstrom-era logic, chips with transistor features measured in 10 billionths of a meter, spearheaded by Intel, TSMC, and Samsung to power the voracious computational demands of artificial intelligence and high-performance computing. At the other end is a massive, simultaneous fortification of the legacy and analog industrial base, technologies rooted in the 45 nanometer to 180 nanometer nodes, which constitute the nervous systems of modern automotive, aerospace, and defense platforms. Bridging these domains is a revolution in compound semiconductors, where materials like silicon carbide, SiC, and gallium nitride, GaN, are replacing silicon to manage the high-voltage realities of the energy transition. This review provides a granular analysis of these investments, dissecting the specific process technologies, financial structures, and construction timelines that define this new era. It explores how the Silicon Desert of Arizona is vying with the Silicon Heartland of Ohio and the emerging memory corridor of New York to anchor the next generation of digital infrastructure. It details how companies are navigating the complex interplay of federal grants, investment tax credits, and the stark realities of construction logistics and labor shortages to erect the most complex machines ever built by humanity. The logic frontier, race for angstroms. The logic sector represents the bleeding edge of semiconductor manufacturing, where the primary objective is the continued scaling of transistor density and performance per watt. The investments in this sector are characterized by their immense scale, often exceeding $20 billion per site, and their reliance on revolutionary changes in transistor architecture, moving from FinFETs to DEAT all-around structures and backside power delivery networks. Intel Corporation remains the central pillar of domestic logic manufacturing, executing its IDM 2.0 strategy to regain process leadership from Asian rivals while simultaneously launching a merchant foundry business, Intel Foundry. The company's investment roadmap is the most aggressive in U.S. history, aiming to deliver 5 process nodes in 4 years and establish a geographically diverse manufacturing footprint. In New Albany, Ohio, Intel is constructing what is intended to be the world's largest silicon manufacturing site. The initial phase involves an investment of approximately $28 billion to construct 2 leading-edge fabrication modules, with a long-term master plan that could accommodate up to 8 fabs and a total investment exceeding $100 billion over the next decade. This site represents a strategic diversification away from coastal tech hubs, anchoring advanced manufacturing in the Midwest. The Ohio facilities are designated as the future home of Intel's Angstrom-era process nodes, specifically Intel 18A and the subsequent Intel 14A. The Intel 18A node is a technological watershed, integrating 2 critical innovations, RibbonFET and PowerVia. RibbonFET is Intel's implementation of gate-all-around transistor architecture, where the gate material completely surrounds the transistor channel, the ribbon, to maximize electrostatic control and reduce leakage at microscopic scales. Power via is a backside power delivery technology that routes power lines through the back of the silicon wafer rather than the front, separating power and signal interconnects to resolve routing bottlenecks and improve signal integrity. Intel has reported that the 18A process is on track for high-volume production in 2025, despite industry skepticism and rumors of yield challenges. The company has moved to reassure stakeholders by noting that a dozen customers are already utilizing the 18A Process Design Kit, PDK. Furthermore, the company has made the tactical decision to bypass the internal manufacturing of the Intel 20A node for its Arrow Lake client processors, outsourcing them to TSMC instead. This move allows Intel to concentrate its engineering resources entirely on the ramp of 18A, framing 20A as a bridge technology rather than a long-term volume node. While Ohio represents the future, the Ocotillo campus in Chandler, Arizona is the operational present. Intel is investing $32 billion here to construct two massive fabs, Fab 52 and Fab 62, creating a mega fab complex. These facilities are the lead vehicles for bringing the 18A node into high-volume manufacturing. Operational updates from late 2024 and 2025 indicate that Fab 52 is effectively complete and has begun limited production. The facility is manufacturing the Panther Lake client processor, Core Ultra Series 3, and the Clearwater Forest server processor. Panther Lake is significant as the first client system-on-chip built on the 18A process, delivering a reported 15% improvement in performance per watt and a 30% increase in transistor density compared to prior generations. Clearwater Forest serves as the lead vehicle for 18A in the data center, leveraging Foveros Direct 3D advanced packaging to bond the 18A compute tiles with 3nm base tiles, showcasing the disaggregated design methodology that defines the future of high-performance logic. Manufacturing the silicon die is only half the battle. Packaging it is the other. In Rio Rancho, New Mexico, Intel has invested $3.5 billion to modernize its Fab 9 and Fab 11X facilities into a dedicated advanced packaging hub. This site is the first high-volume manufacturing location for Foveros 3D packaging technology, which allows logic die to be stacked vertically, enabling the creation of complex chiplets like those found in the Ponte Vecchio and Clearwater Forest processors. Supporting all these efforts is the D1X research facility in Hillsboro, Oregon. Intel is investing heavily here to install the world's first high numerical aperture, high NA, extreme ultraviolet lithography tools from ASML. These massive machines, which cost hundreds of millions of dollars each, are capable of printing features with a resolution of 8 nanometers, a prerequisite for the Intel 14A node and beyond. Oregon remains the source of the copy exactly methodology, ensuring that the processes developed in the Pacific Northwest can be replicated precisely in Arizona and Ohio. The project undertaken by TSMC in Phoenix, Arizona, represents the largest foreign direct investment, or FDI, in a greenfield project in the history of the United States. Initially announced in 2020 as a $12 billion endeavor, the scope of the investment has ballooned dramatically in response to the incentives provided by the CHIPS Act and the voracious demand for artificial intelligence, or AI, and high-performance computing, or HPC, silicon. By 2024, TSMC had committed to a total capital expenditure of over $65 billion for the Arizona site. This investment is structured around the construction of 3 distinct fabrication facilities, or fabs, within a massive campus that TSMC refers to as a gigafab cluster. The timeline and technological roadmap for these facilities reveal a strategy of progressive advancement, mirroring the rapid evolution of semiconductor nodes. The sheer scale of this undertaking transforms the North Phoenix landscape, turning acres of desert scrub into one of the most technologically advanced manufacturing zones on Earth. The first fab, designated Fab 21 Phase 1, was designed to introduce 4-nanometer process technology to the United States. While 4-nanometer is an advanced node used in current-generation smartphones and processors, it serves as the foundational step for the site's capabilities. Construction on this facility began in April 2021, and despite initial delays, it successfully entered high-volume manufacturing in late 2024. This facility serves as the proving ground for TSMC's ability to transplant its rigorous manufacturing processes across the Pacific, a test that was viewed with skepticism by industry observers, given the high costs of U.S. operations. The second fab represents a leap to the 3-nanometer node, the current state-of-the-art for mass-produced consumer electronics. Construction on the shell of this facility was completed by 2025, with high-volume production targeted for 2028. This facility is critical for customers like Apple and NVIDIA, who require the thermal and performance benefits of the 3-nanometer node for next-generation devices. The progression to 3-nanometer in Arizona ensures that the U.S. supply chain does not remain perpetually a generation behind Taiwan, addressing a key criticism of earlier reshoring attempts. The third fab, announced in April 2024, pushes the technological envelope further with plans to manufacture 2-nanometer chips and employ the revolutionary A16 process technology. The A16 node utilizes backside power delivery, a complex architectural change that improves power efficiency and speed, marking the first time such cutting-edge experimental technology has been earmarked for U.S. production concurrently or shortly after its debut in Taiwan. This inclusion of the A16 node is significant. It signals that the Arizona site is not merely a backup facility for older technology, but a primary node in TSMC's global bleeding-edge capacity. By 2025, buoyed by the ratification of funding and the stabilization of early operations, TSMC's long-term vision for the site expanded even further. Reports indicated a roadmap potentially growing to 6 fabs, 2 advanced packaging facilities, and a dedicated research and development center, pushing the total potential investment toward a staggering $165 billion over the project's lifetime. This expansion would cement Arizona's status not just as a manufacturing hub, but as a center of gravity for the entire global semiconductor ecosystem, potentially rivaling the Hsinchu Science Park in scale and importance. The financial architecture supporting TSMC's Arizona expansion is a complex amalgamation of direct grants, loans, and tax incentives. In November 2024, the U.S. Department of Commerce finalized a direct funding award of up to $6.6 billion for TSMC Arizona. This grant is performance-based, with disbursements tied to specific construction, production, and commercial milestones, ensuring the taxpayer funds are leveraged to guarantee project completion. The negotiation of this award was a protracted process, reflecting the government's need to secure strict compliance and the company's need to offset the cost gap between U.S. and Asian manufacturing. Beyond the direct grant, the agreement provides TSMC with access to up to $5 billion in low-interest loans, drawn from the $75 billion loan authority established by the CHIPS Act. These loans provide critical liquidity for the massive capital expenditures required for equipment procurement and facility construction. In an industry where a single ultraviolet lithography machine can cost upwards of $150 million, access to favorable capital markets is a decisive factor in investment viability. Perhaps the most lucrative component of the financial package, however, is the investment tax credit. Under the Advanced Manufacturing Investment Credit established by the CHIPS Act, companies are eligible for a tax credit equal to 25% of their qualified capital investment. For a project with a capital intensity of $65 billion and potentially rising to $165 billion, the value of this credit is immense. Analysts estimate that TSMC could reap between $7 and $8 billion in tax credits for the initial phases alone, with the potential for tens of billions more if the expansion to 6 fabs is realized. This tax credit, which is uncapped, serves as the long-term economic stabilizer for the project, offsetting the structurally higher costs of building and operating fabs in the United States compared to Taiwan. Critics of the subsidies have pointed out that the ITC essentially uncaps the government's liability, potentially costing the Treasury far more than the headline grant figures suggest. But proponents argue this is the necessary price of sovereignty. The journey to bring Fab 21 online was not merely a technical challenge, but a profound sociological collision between the intense military-style efficiency of East Asian semiconductor manufacturing and the regulatory and labor norms of the American construction industry. This friction led to significant delays and public disputes that threatened to derail the project's timeline and exposed deep fissures in the globalized workforce model. The core of the conflict arose from differing expectations regarding work hours, hierarchy, and speed. TSMC's success in Taiwan is built upon a culture of extreme dedication, where engineers and construction crews work long hours, often 12-hour shifts, and are available on call to address issues immediately. When this management philosophy was imported to Arizona, it clashed violently with the norms of the U.S. workforce. American workers, including highly skilled union tradespeople, prioritized work-life balance, safety regulations, and a less hierarchical communication style. Tensions boiled over in 2023 when TSMC delayed the start of production from 2024 to 2025, citing a shortage of skilled labor in the Phoenix area capable of installing the sophisticated cleanroom equipment. To mitigate this, TSMC sought to import hundreds of specialized workers from Taiwan to expedite the construction. This move incited a fierce backlash from the Arizona Building and Construction Trades Council, or AZBTC, a coalition of labor unions. Labor leaders characterized the move as an attempt to undermine American wages and replace local workers with cheaper foreign labor, labeling the skills shortage claim as inaccurate and offensive. Reports from the ground described a chaotic work environment fueled by mutual misunderstanding. American workers complained of disorganized management, constant changes to blueprints, and safety protocols that they felt were inferior to U.S. OSHA standards. Specific allegations surfaced in class action lawsuits and worker testimonials. One lawsuit alleged that a technician found a rubber chicken hanging over a black colleague's desk, interpreting it as a racially hostile act, while others reported being called lazy and stupid by managers accustomed to the grueling pace of Taiwanese fabs. Another report detailed how workers were ordered to perform tasks that violated safety norms, such as climbing struts without scaffolding, practices that would result in immediate dismissal on a unionized American site. Conversely, Taiwanese managers viewed the American workforce as slow, difficult to manage, and lacking the flexibility required for such a high-stakes project. They expressed frustration with the rigidity of American labor roles and the refusal of workers to perform tasks outside their specific job descriptions. The cultural disconnect was exacerbated by language barriers. Reportedly, meetings were held exclusively in Mandarin, alienating American staff and creating a bifurcated workforce where information did not flow freely. The dispute was eventually resolved in late 2023 through a landmark agreement between TSMC and the ASBTC. The accord established a framework for collaboration where TSMC committed to prioritizing local hiring and investing in workforce training programs, while the unions acknowledged the necessity of specialized foreign talent for specific, highly technical tasks. This détente allowed construction to proceed, although the initial culture shock remains a cautionary tale for future reshoring efforts, highlighting that transferring technology is far easier than transplanting corporate culture. Despite the tumultuous construction phase, the operational debut of TSMC Arizona has been a resounding technical success, confounding skeptics who believed that U.S. manufacturing could never match the efficiency of Taiwan. By late 2024 and early 2025, reports emerged that the yield rates, the percentage of functional chips produced per wafer, at the Arizona fab were comparable to, and in some cases even higher than, those at TSMC's flagship fabs in Taiwan. Specifically, the first phase of Fab 21, producing 4 nm chips, reportedly achieved yield rates in the 65 to 70% range for early risk production, and eventually climbed to match the high standards of Taiwan operations. Some analyses even suggested a yield rate approximately 4% higher than comparable facilities in Tainan, a statistic that effectively debunked the myth that American labor could not execute the precision manufacturing required for modern semiconductors. This yield miracle suggests that the intense scrutiny and the deployment of TSMC's most experienced engineers to Arizona to troubleshoot the startup phase paid dividends, creating a facility that is a clone of its Taiwanese parents in quality, if not in cost. This operational success has solidified Arizona's status as a burgeoning silicon desert. The fab is now producing the A16 Bionic chip for Apple products and processors for AMD, proving that the supply chain, while young, is functional. The success of Fab 21 has also triggered a secondary wave of investment from the broader supply chain. Companies like Amkor Technology have broken ground on advanced packaging facilities in the region to provide the last mile of chip production, ensuring that wafers manufactured in Arizona do not need to be shipped back to Asia for final assembly. This localization of packaging is a critical development. Without it, the Made in USA chip would still require a round-trip ticket across the Pacific, negating the supply chain security goals of the CHIPS Act. While TSMC established its foothold in the desert Southwest, Samsung Electronics doubled down on its long-standing presence in Texas. Having operated a fab in Austin since 1996, Samsung announced in 2021 a massive expansion into the nearby municipality of Taylor, Texas. This project, valued at over $40 billion, was conceived as a comprehensive semiconductor ecosystem designed to rival TSMC's influence and capture the growing demand for North American-made chips. The Taylor site is significantly larger than the existing Austin campus, representing a greenfield development that will eventually house 2 leading-edge logic fabs, a research and development facility, and an advanced packaging plant. The strategic vision for Taylor is to serve as a hub for essential chips powering high-growth sectors such as artificial intelligence, 5G communications, and automotive electronics. The scale of the Taylor project is intended to be transformative for the local economy, turning a small agricultural community into a high-tech powerhouse, a transition that brings both economic windfalls and infrastructure strains. In April 2024, the Biden-Harris administration and Samsung signed a preliminary memorandum of terms providing up to $6.4 billion in direct funding under the CHIPS Act. Like the TSMC award, this grant is designed to catalyze private investment, with Samsung committing to invest more than $40 billion in the region in the coming years. However, the finalization of this award saw some adjustments. By late 2024, the finalized grant amount was reported as $4.75 billion, lower than the initial $6.4 billion figure, reflecting adjustments based on market conditions and the scope of investment. This reduction coincided with Samsung's broader struggles in the foundry market and a recalibration of its investment efficiency. Despite the lower grant total, Samsung remains a massive beneficiary of the 25% investment tax credit, which applies to the billions of dollars spent on facility construction and equipment installation. The reduction in the grant amount serves as an indicator of the complex negotiations occurring behind closed doors, where the government attempts to balance its desire for capacity with the need to be a prudent steward of taxpayer money, particularly when market dynamics shift. The most dramatic development in the Samsung-Taylor saga is the strategic pivot regarding the technology the plant will produce. Originally, the Taylor fab was slated to begin operations in 2024, producing 4nm chips. However, rapidly shifting market dynamics and intense competition from TSMC forced a radical change in strategy. By 2024, it became clear that the demand for 4nm chips was not sufficient to justify the massive operational costs of the new fab, particularly as major customers like Qualcomm and Nvidia continued to favor TSMC's superior yields. Faced with the prospect of opening a multi-billion-dollar facility with no customers, Samsung made the bold decision to delay the opening of the Taylor fab to 2026 and upgrade its capabilities to produce 2nm chips. This transition is not merely a software update. It requires different equipment and a fundamental change in manufacturing processes. The shift aims to position the Taylor facility at the absolute bleeding edge of technology, capable of producing the chips required for the next generation of AI accelerators. However, this pivot has come at the cost of time. The delay from a 2024 opening to 2026 has been a significant setback for the Biden administration's goal of rapid domestic capacity expansion, leaving a 2-year gap where the massive facility sits largely dormant while waiting for the market and technology to align. The backdrop to the Taylor delays is a broader crisis within Samsung's foundry business. For years, Samsung has struggled to match the yield rates of its rival TSMC. While TSMC consistently achieves yields of 90% or higher on its advanced nodes, Samsung has reportedly struggled with yields stagnating around 50% for its 3nm process. Low yield rates are catastrophic in the contract chip-making business. They increase the cost per chip for the customer and create uncertainty regarding supply. This yield disparity was the primary driver behind the Google shock, the decision by Google to switch production of its Tensor smartphone chips from Samsung to TSMC for the Pixel 10 and beyond. Losing a high-profile customer like Google, which had been a key partner for Samsung's logic division, was a severe blow to confidence. The loss was attributed not just to yield, but also to Samsung's lack of semiconductor design assets and the inherent conflict of interest between Samsung's foundry business and its own smartphone division, which competes directly with Google's Pixel line. Furthermore, Qualcomm, another longtime Samsung partner, shifted its Snapdragon 8 Gen 4 orders exclusively to TSMC, citing performance and yield advantages. These losses left the Taylor fab in a precarious position, built to serve customers who were fleeing to the competition. The narrative surrounding Samsung's foundry business became one of existential risk. Without external customers, the foundry risked becoming merely a captive manufacturer for Samsung's own Exynos chips, a model that cannot sustain the massive capital requirements of modern fabs. Facing a dwindling order book, Samsung has bet its future on the 2nm node and a new partnership with Tesla. In July 2025, reports confirmed a landmark $16.5 billion contract with Tesla to produce the automaker's next-generation AI6 chips at the Taylor facility. This deal represents a massive validation of Samsung's turnkey strategy, where it offers logic manufacturing, memory production, HBM, and advanced packaging all under one corporate roof, a synergy TSMC cannot fully match as it does not manufacture memory. The Tesla contract provides the anchor tenant the Taylor fab desperately needed. It also signals that the automotive AI sector may be Samsung's path to redemption. To support this, Samsung is accelerating its 2nm roadmap, aiming to achieve mass production capability by 2026. The company is also aggressively cutting prices, reportedly offering 2nm wafers at a 33% discount compared to TSMC to attract cost-sensitive customers. This pricing strategy, combined with the one-stop shop appeal for AI clients who need high-bandwidth memory integrated directly with their processors, offers a potential route out of the crisis. Just as TSMC is building a supply chain in Arizona, Samsung is replicating its South Korean ecosystem in Central Texas. The Samsung effect has drawn numerous suppliers to the region, transforming the industrial geography of Williamson County. Hanyang ENG, a critical supplier of piping and chemical systems, has established a headquarters in Cedar Park and is actively working on the Taylor clean rooms. LS Electric, a power systems giant, has signed massive contracts to supply the electrical infrastructure for the Taylor plant and other data centers in the region, solidifying the energy backbone required for such energy-intensive operations. Additional partners like Dongjin Semichem, Solbrain, and FST are establishing production bases in Texas to supply photoresists, etchants, and other critical consumables. This localization of the supply chain is a critical requirement for the long-term viability of the project. By bringing materials and equipment suppliers closer to the fab, Samsung aims to reduce logistics costs and improve reaction times, mimicking the tight-knit efficiency of its operations in Yongyan and Hwaseong. Furthermore, iMarket America is developing the Gradient Technology Park, a massive industrial complex designed to house these suppliers, further cementing the Korean industrial footprint in Texas. FinFET versus GAA. To understand the stakes of the competition between TSMC Arizona and Samsung Taylor, one must understand the technology they are fighting to master. The current era of semiconductor manufacturing is defined by a transition in transistor architecture, as significant as the shift from vacuum tubes to solid state. For the past decade, the industry has relied on FinFET, Fin Field Effect Transistor technology. In a FinFET, the channel through which current flows is raised into a vertical fin, allowing the gate to wrap around it on three sides. This provided better control over current flow than planar transistors, enabling the shrinking of nodes down to 3 nanometers. However, as transistors continue to shrink, FinFETs are reaching their physical limits. The fin structure can no longer prevent current leakage effectively at the atomic scale required for 2 nanometer chips. The solution is gate-all-around technology. In a GAA transistor, the gate completely surrounds the channel on all 4 sides. This is achieved by stacking horizontal nanosheets on top of one another. GAA offers superior electrostatic control, allowing for higher performance and lower power consumption, critical attributes for the battery-draining AI applications of the future. The transition allows for more precise control of the current, effectively shutting off the transistor more completely when it is not in use, drastically reducing the leakage power that plagues modern processors. This technological transition is where the strategies of Samsung and TSMC diverge sharply. Samsung chose to be the first mover, introducing GAA technology, which it calls MBC FET, or Multi-Bridge Channel FET, at the 3 nanometer node. This was a high-risk gamble. By adopting a new architecture early, Samsung hoped to gain a lead in experience. However, the complexity of the new process contributed to the low yield rates that have plagued its 3 nanometer production. The first-mover advantage turned into a first-mover disadvantage as Samsung struggled to stabilize the process, while TSMC continued to churn out high-yield 3-nanometer chips using the older FinFET technology. TSMC, conversely, adopted a more conservative approach. It chose to stick with the proven FinFET architecture for its 3-nanometer node, N3, prioritizing yield and reliability over architectural novelty. TSMC plans to transition to GAA nanosheets only at the 2-nanometer node, N2. This strategy has paid off in the short term, as TSMC's stable 3-nanometer FinFET process allowed it to capture the vast majority of the market for current generation chips. The battle for 2026 and beyond will be fought on the 2-nanometer GAA landscape. Samsung hopes that its early pain with 3-nanometer GAA will translate into a smoother ramp-up for 2 nanometers, allowing it to leapfrog TSMC. TSMC, however, is confident that its manufacturing prowess will allow it to master GAA quickly when it debuts its N2 node in 2025-2026. The Arizona and Taylor fabs are the physical arenas where this abstract technological contest will be decided. Additionally, the introduction of backside power delivery, BSPDN, adds another layer of complexity. TSMC's A16 node and Intel's 18A, PowerVia, utilize this technology to route power through the back of the wafer, freeing up space on the front for logic connections. This is a critical enabler for further scaling, and its successful implementation in Arizona via the A16 node will be a key differentiator in the latter half of the decade. The analog and mature node backbone. Texas Instruments. While sub-5-nanometer logic captures the imagination, the modern economy runs on analog chips, power management ICs, or PMICs, and microcontrollers, or MCUs. These components, often built on mature nodes ranging from 45 nanometers to 180 nanometers, are the unheralded workhorses of the automotive, industrial, and defense sectors. A shortage of a single $1 analog chip can halt the production of a $50,000 electric vehicle, making capacity in this sector strategically vital. Texas Instruments, or TI, is executing a distinct strategy focused on cost leadership in analog processing. The scale of the ambition currently being realized by Texas Instruments, or TI, is difficult to overstate. Headquartered in Dallas, TI has long been the bellwether of the analog industry, a sector characterized by long product life cycles and stable margins rather than the boom and bust obsolescence of the digital logic market. Yet, TI's current strategy is one of aggressive, capital-intensive expansion that rivals the largest infrastructure projects in American history. The company has committed to a roadmap that could see over $60 billion invested across its manufacturing footprint, with the explicit goal of bringing more than 95% of its manufacturing capacity in-house by 2030. To understand why TI is pouring concrete in Sherman, Texas, and Lehi, Utah, we must look at the geometry of the silicon wafer. For decades, the standard size for manufacturing analog chips was the 200mm or 8-inch wafer. These circular discs of silicon were sufficient for the larger transistors used in power management and signal processing. However, TI has bet its future on a transition to 300mm or 12-inch wafers. The mathematics of this shift are compelling. A 300mm wafer has more than twice the surface area of a 200mm wafer. Because analog chips are relatively large compared to digital transistors, the edge loss, the wasted space near the curved edge of the wafer, is proportionally smaller on the larger disk. This geometric advantage allows TI to produce approximately 2.3 times as many chips per wafer as its competitors using older technology. This creates a structural economic moat. Once the massive capital cost of the factory is amortized, TI can produce an unregulated analog chip for pennies less than its rivals. In a market where billions of units are sold, those pennies compound into billions of dollars in gross margin. This cost advantage is the engine driving the bulldozers in North Texas. The epicenter of this strategy is located in Sherman, Texas, a city near the Oklahoma border that has been transformed into a hub of high-tech manufacturing. TI's site in Sherman is not merely a factory, it is a mega-site designed to house up to 4 interconnected fabrication plants, or fabs, operating as a single organism. The timeline of this development has been relentless. Ground was broken in 2022, and by December 17, 2025, TI officially began production at the first facility, designated SM1. The ribbon-cutting ceremony, attended by Texas Governor Greg Abbott and TI CEO Haviv Ilan, marked the transition from construction to operation. SM1 is a behemoth, a clean room environment spanning hundreds of thousands of square feet, where automated overhead transport systems zip cassettes of wafers between processing tools. But SM1 is just the first movement of the symphony. The shell for the second facility, SM2, was already completed by the time SM1 opened its doors, standing ready to be equipped with tools as market demand dictates. The master plan allows for 2 additional fabs, SM3 and SM4, to be constructed on the same site. This modular approach allows TI to scale up production without the multi-year delays associated with starting a greenfield project from scratch. When fully operational, the Sherman campus will produce tens of millions of chips every day. The strategic importance of Sherman is underscored by the federal support it has garnered. In 2024, the Department of Commerce awarded TI up to $1.6 billion in direct funding under the CHIPS Act, specifically to support the construction of the Sherman and Utah sites. Furthermore, TI expects to claim between $6 billion and $8 billion in investment tax credits from the U.S. Treasury, a 25% reimbursement on the qualified capital expenditures that makes the sheer size of the project financially viable. The Sherman project stands on the shoulders of TI's existing infrastructure in Richardson, Texas. It was here, with the RFAB1 facility, that TI first proved the viability of manufacturing analog chips on 300mm wafers in 2009. The success of RFAB1 gave the company the confidence to build RFAB2, which is currently ramping up to full production. The proximity of the Richardson and Sherman sites creates a massive ecosystem of talent and suppliers in North Texas. Engineers, technicians, and specialized maintenance crews can move between the sites, creating a depth of human capital that is difficult for competitors to replicate. This regional concentration reduces logistics costs and allows for the sharing of best practices in real time, effectively turning the region north of Dallas into a Silicon Prairie focused on the foundational chips that power the modern world. While Texas is the heart of TI's operations, the company has established a second 300mm stronghold in the Silicon Slopes of Lehi, Utah. This expansion began with an opportunistic acquisition. In 2021, TI purchased an existing 300mm fab, LFAB1, from Microchip Technology, a memory chip manufacturer that was exiting the specialized 3D X-point market. For TI, the Lehi acquisition was a shortcut to capacity. Instead of waiting 3 years to build a shell, they acquired a fully built cleanroom that only needed to be retooled for analog processes. But TI did not stop at acquisition. In February 2023, the company announced an $11 billion investment to build a second fab, LFAB2, immediately adjacent to the first. This project represents the largest single economic investment in the history of Utah. The Lehi expansion is particularly notable for its environmental engineering. Semiconductor manufacturing is a thirsty business, consuming millions of gallons of ultra-pure water. In the arid climate of Utah, water stewardship is an existential requirement. The new LFAB 2 facility is designed to recycle water at nearly double the rate of the existing fab, employing advanced filtration and reclamation systems to minimize its draw on the local watershed. Once completed, the two Lehi fabs will operate as a single entity, sharing chemical delivery systems and utility infrastructure. This unification allows for extreme efficiency. The Federal CHIPS Act funding explicitly covers the Lehi expansion alongside Sherman, recognizing the strategic value of having a geographically diverse manufacturing base that is not solely concentrated in a single state. The limiting factor in this massive expansion is not silicon or steel, but human talent. Operating a modern 300mm fab requires a workforce with a specific and rare set of skills, from the PhD process engineers who tweak the plasma etch recipes to the equipment technicians who maintain the robotic handlers. TI has committed to creating approximately 3,000 new jobs in Sherman alone, with thousands more in Utah. To ensure these roles can be filled, the company has integrated itself into the local education systems. In Utah, TI is investing $9 million directly into the Alpine School District to improve student outcomes and foster interest in STEM careers. Similarly, the Federal CHIPS Award includes a dedicated $10 million fund for workforce development, which TI is using to partner with community colleges in Texas and Utah to create certification programs specifically tailored to semiconductor manufacturing. GlobalFoundries. If Texas Instruments is the king of internal manufacturing, GlobalFoundries, GF, is the mercenary army of the industry. A foundry that manufactures chips for other companies, including national defense contractors and automotive giants. Headquartered in Malta, New York, GF has positioned itself as the trusted foundry of the Western world, a designation that has attracted billions in federal and state support to its campuses in New York and Vermont. The story of GF's expansion is inextricably linked to the industrial policy of New York State. The company's Fab 8 in Malta, New York, is one of the most advanced manufacturing sites in the United States. Following the passage of the CHIPS Act, GF secured a $1.5 billion direct funding award from the Department of Commerce to expand its U.S. footprint. This federal largesse was matched by the state. Under New York's Green CHIPS program, GF was awarded $575 million in tax credits. These credits are performance-based, tied to strict sustainability goals, including the use of renewable energy and the reduction of greenhouse gas emissions. This aligns with GF's broader corporate strategy to market its chips not just as made in USA, but as sustainably made. The expansion at Malta is three-pronged. First, GF is expanding the capacity of the existing Fab 8 to serve the automotive industry. As cars transition to electric and autonomous architectures, the demand for high-reliability microcontrollers and sensors has exploded. GF has signed long-term agreements with General Motors to provide a dedicated supply of these chips, effectively integrating the fab into GM's supply chain. Second, GF is constructing a new state-of-the-art fab on the same campus. This new facility is designed to meet the demand for essential chips in aerospace, defense, and AI at the edge applications. Unlike the massive AI training clusters that use 3-nanometer chips, edge AI devices like smart cameras or industrial robots rely on the mature, power-efficient nodes that GF specializes in. Third, and perhaps most strategically significant, is the creation of the New York Advanced Packaging and Photonics Center within the Malta facility. Announced in early 2025, this center addresses a glaring hole in the U.S. supply chain: packaging. For decades, chips manufactured in the US were shipped to Southeast Asia to be cut, tested, and encased in plastic. This added weeks to the supply chain and introduced security risks. By bringing advanced packaging onshore, specifically for silicon photonics, which use light instead of electricity to move data, GF is creating an end-to-end secure corridor for the most sensitive US technologies. While New York focuses on silicon, GF's facility in Essex Junction, Vermont is spearheading a revolution in material science. This fab, which GF acquired from IBM, has been in operation for nearly 70 years. In the fast-moving world of tech, it should be a museum. Instead, it is being reborn as the premier manufacturing site for gallium nitride. GaN is a wide bandgap semiconductor material that is vastly superior to silicon for handling high power and high frequencies. It is the magic material that allows the power brick for your laptop to be half the size it used to be, and it is essential for the efficient operation of electric vehicle chargers and 5G cellular towers. The CHIPS Act award includes specific funding to modernize the Vermont fab for high-volume GaN production. This is a difficult engineering challenge. GaN crystals behave differently than silicon, and processing them requires specialized tools and recipes. By mastering this volume production in Vermont, GF is positioning the US to dominate the next generation of power electronics, reducing reliance on foreign suppliers for the critical components of the green energy transition. A recurring theme in GF's expansion is its deep integration with the US defense apparatus. The Department of Defense, DoD, has long worried about the security of the chips used in its weapon systems. A chip with a hidden back door or a kill switch could render a fighter jet useless in combat. GF's facilities in New York and Vermont are accredited as trusted foundries by the US government. This means they meet rigorous security standards regarding personnel, physical security, and supply chain integrity. GF has entered into a strategic partnership with Lockheed Martin to manufacture the chips used in the defense contractor's most advanced systems. This partnership ensures that the guidance systems for missiles, the radar arrays for destroyers, and the communications gear for special forces are manufactured within a secure domestic enclave. The expansion in Malta is not just an economic project, it is a national security imperative. Analog devices. In the Pacific Northwest, amidst the silicon forest of Oregon and Washington, Analog Devices, Inc. (ADI) is pursuing a strategy that differs markedly from the fortress building of TI or the foundry services of GF. ADI operates a hybrid manufacturing model, blending internal production for its most proprietary technologies with external partners for standard components. However, the post-pandemic reality has pushed ADI to tilt this balance back toward internal, domestic production. ADI's campus in Beaverton, Oregon is a testament to the longevity of analog technology. The fab was built in 1978. In the digital world, a factory from the disco era would be obsolete. In the analog world, it is a vintage asset ripe for modernization. In July 2023, ADI announced an investment of over $1 billion to expand the Beaverton facility. This capital injection is not just for maintenance, it is a transformative upgrade. The investment is expanding the clean room space to approximately 118,000 square feet and, crucially, converting the facility to a full 8-inch, 200mm wafer fab. The focus of this expansion is on the 180 nanometers to 350 nanometer technology nodes. To a layperson accustomed to hearing about 3-nanometer chips, 180 nanometers sounds ancient. But in the world of industrial sensors and medical devices, 180 nanometers is the Goldilocks node, large enough to handle high voltages and robust enough to survive harsh environments, yet small enough to integrate significant computing power. By onshoring the production of these specific nodes, ADI is insulating its customers in the healthcare and industrial sectors from the vagaries of the international supply chain. ADI's investment extends across the Columbia River to its facility in Camas, Washington. This site is receiving upgrades focused on environmental sustainability, specifically to reduce the use of solvents in the manufacturing process. The Camas expansion aims to increase the facility's capacity by 70%, further strengthening the regional cluster. In January 2025, the Department of Commerce signed a preliminary agreement to provide ADI with up to $105 million in CHIPS Act funding. While smaller than the billion-dollar grants for megafabs, this funding is highly efficient. It targets the brownfield modernization of existing sites, which offers a faster return on investment than building from scratch. This funding is split between the Beaverton, Camas, and a third site in Chelmsford, Massachusetts, reinforcing a coast-to-coast network of analog capability. Recognizing that the shortage of skilled technicians is as acute as the shortage of chips, ADI has taken a direct approach to education. The Beaverton facility hosts the Semiconductor Advanced Manufacturing University, SAMU. This is not a traditional university. It is an internal training center designed to take individuals from diverse backgrounds, including military veterans and people re-entering the workforce, and turn them into semiconductor maintenance technicians in 8 weeks. The curriculum is hyper-focused on the specific equipment used in ADI's fabs. Students learn to troubleshoot the vacuum pumps, calibrate the lithography steppers, and handle the delicate wafers. By building its own internal university, ADI is creating a bespoke workforce, ensuring that the human capital in the Silicon Forest keeps pace with the physical capital being installed. Microchip Technology. The story of the U.S. semiconductor resurgence is generally one of optimism and expansion. However, the experience of Microchip Technology serves as a sobering counter-narrative, illustrating the friction that occurs when long-term government policy collides with the short-term brutality of the business cycle. Microchip Technology is a leading manufacturer of microcontrollers, the small specialized computers that act as the brains for specific tasks in appliances, cars, and weapons. In early 2024, the company seemed poised to be a major beneficiary of the CHIPS Act. The Department of Commerce announced a preliminary agreement to award Microchip $162 million in incentives. The plan was robust. $90 million was allocated to Project Hydrogen, a modernization of the company's fab in Colorado Springs, Colorado. The goal was to retool the facility to produce silicon carbide (SiC) and silicon products on 8-inch wafers, critical for military and aerospace applications. The remaining $72 million was destined to Gresham, Oregon, to triple the output of a facility that produces the mature node chips used in everything from washing machines to guided missiles. However, the semiconductor industry is notoriously cyclical. The shortage of 2021 led to panic buying. Customers double-ordered chips to ensure they would have enough. When the economy cooled in 2024, those customers stopped buying to work through their bloated inventories. The industry swung violently from shortage to glut. Microchip was hit hard. With revenue falling and inventory piling up, the company had to cut costs. This created a conflict with the CHIPS Act grant, which is typically tied to capital expenditure milestones. If a company stops building, it can't claim the grant. In December 2024, Microchip CEO Steve Sanghi announced that the company would abruptly stop pursuing the $162 million grant and put negotiations with the government on hold for now. This was a stunning development. The company also announced the closure of a factory in Tempe, Arizona, to consolidate operations. This pause has had immediate local consequences. In Gresham, the expansion was not just about federal money, it was also tied to state incentives from the Oregon CHIPS program. These state grants often have job creation requirements. With the expansion slowed, Microchip reported creating 0 new jobs in Gresham between January and June 2024, and even had to furlough workers. However, pause is not cancel. The company has stated it still plans to complete the expansions when market demand returns. The structural need for domestic microcontrollers in defense and automotive sectors hasn't changed, only the timing. The clean rooms in Gresham and Colorado remain strategic assets, but their growth trajectory has been flattened by the inventory correction. This episode highlights the difficulty of synchronizing static government 5-year plans with the dynamic, fluctuating reality of the global market. Despite the pause, Microchip remains deeply embedded in the Gresham community. The company has maintained its partnerships with local educational institutions such as Mount Hood Community College. The Elevate Careers program, a partnership with the college, recently graduated its first cohort of semiconductor technicians. Microchip also works with the Rosemary Anderson High School and the Portland Opportunities Industrialization Center to create a pipeline for students from underrepresented backgrounds to enter the high-tech workforce. These grassroots efforts suggest that while the capital expansion may be delayed, the commitment to the region's human infrastructure remains intact. Power and compound semiconductors. Wolfspeed is leading the global transition from 150mm 6-inch wafers to 200mm 8-inch wafers. To understand the magnitude of Wolfspeed's journey, one must first understand the physics that drove their ambition. For half a century, silicon has been the undisputed king of semiconductors. It is abundant, cheap, and well understood. However, as the world pivots toward electrification, specifically electric vehicles and high-performance renewable energy grids, silicon begins to hit its physical limits. When you push too much voltage through standard silicon, it leaks energy as heat. In an electric car, that heat is wasted range. In a data center, it is wasted electricity and increased cooling costs. Enter silicon carbide. This compound material, a synthesis of silicon and carbon, is a wide bandgap semiconductor. In layman's terms, it can withstand much higher voltages and temperatures than silicon before breaking down. A power inverter made with silicon carbide is more efficient, lighter, and smaller than one made with silicon. For an electric vehicle manufacturer, switching to silicon can mean adding 5 to 10% more range to a vehicle without increasing the battery size. In the hyper-competitive automotive market, that advantage is worth billions. Wolfspeed, headquartered in Durham, North Carolina, was not a diversified chip giant dabbling in this new technology. It was a pure-play pioneer. It bet everything on the belief that the world would inevitably switch to silicon carbide. But to make that switch feasible, the cost of the material had to come down. And to bring the cost down, Wolfspeed had to do something no one had ever done before: mass-produce silicon carbide on 200mm or 8-inch wafers. The heart of Wolfspeed's strategy and the source of its near-existential crisis is the John Palmour Manufacturing Center for Silicon Carbide, affectionately known as the JP. Located in Chatham County near Siler City, North Carolina, this facility represents one of the most ambitious industrial projects in the history of the American South. Announced in September 2022, the Siler City project was designed to be the world's largest materials factory for silicon carbide. The statistics are staggering. A $5 billion total investment spread across a 445-acre site with a facility footprint exceeding 2 million square feet. The strategic goal was simple but daunting: increase Wolfspeed's materials production capacity by tenfold. The facility is dedicated to crystal growth. Unlike standard silicon, which is drawn from a melt, silicon carbide must be grown as a crystal at incredibly high temperatures, over 2,500 degrees Celsius, in a process that takes weeks. These crystals, boules, are then sliced into wafers. The JP was built to produce 200mm wafers, which are 1.7 times larger in surface area than the industry standard 150mm wafers. The math is brutal and beautiful. A larger wafer yields more chips at the edge, drastically lowering the cost per chip. Wolfspeed's thesis was that whoever mastered 200mm first would control the market. Construction began in a boom time, but dragged on into a bust. By late 2025, the facility was nearing completion, but the timeline had slipped. Originally slated for 2024, the full certificate of occupancy was pushed to the first half of calendar year 2025. The delays were not just about pouring concrete, they were about survival. As the global EV market cooled in 2024, particularly in Europe and North America, Wolfspeed faced a liquidity crunch. They had to slow down the ramp, the speed at which they installed tools, to conserve cash. Yet they could not stop. The factory was the future. By December 2025, they had hired over 200 employees to begin the initial crystal growth testing, a fraction of the 1,800 workers expected at full capacity, but a sign of life nonetheless. The decision to build in Siler City was not made in a vacuum. It was the result of a coordinated effort by state and federal governments to buy this capacity for the United States. North Carolina offered a package worth approximately $1 billion, including a job development investment grant of $86 million. But the true lifeline was the Federal CHIPS and Science Act. In October 2024, Wolfspeed signed a preliminary memorandum of terms with the Department of Commerce for up to $750 million in direct grants. This federal stamp of approval was critical, not just for the cash, but for the confidence it gave private investors. On the heels of the CHIPS announcement, a consortium of lenders led by Apollo agreed to provide an additional $750 million in private financing. The government had essentially co-signed Wolfspeed's mortgage. If Siler City is the mine, the Mohawk Valley Fab in Marcy, New York is the forge. Opened in April 2022, this facility holds the distinction of being the world's first and largest fully automated 200mm silicon carbide fabrication plant. It is here that the blank wafers from North Carolina are processed into active computer chips. Being first is expensive. For nearly 2 years, the Mohawk Valley Fab sat largely idle, a Ferrari in a garage with no fuel. The facility was designed for 200mm wafers, but Siler City, the source of those wafers, was not yet ready. Wolfspeed had to try to produce limited quantities of 200mm wafers at its older R&D lines in Durham, which was inefficient and slow. This mismatch led to massive underutilization costs. In the accounting of manufacturing, a factory costs millions of dollars a day to run, whether it produces 1 chip or 1 million. If it runs at 10% capacity, the cost per chip is astronomical. In the first quarter of fiscal year 2026 alone, Wolfspeed reported $47 million in underutilization costs. This was a heavy anchor on their balance sheet, dragging them into deep losses quarter after quarter. However, by late 2025, the tide began to turn. As Siler City began its initial output, the Mohawk Valley Fab started to hum. Revenue from the facility reached $97 million in the quarter ending September 2025, a year-over-year doubling. The bet was finally starting to pay off, proving that the automated 200mm process worked if you could just get the wafers. New York State's involvement in this project was substantial. Empire State Development provided up to $500 million in capital grants, but the state went further, treating the project as a catalyst for regional revitalization. The Mohawk Valley Empowers program, a $10 million workforce initiative, was launched to turn the local population into semiconductor technicians. Wolfspeed integrated itself into the SUNY system, funding scholarships and curriculum development to ensure that local graduates could operate the highly automated tools inside the fab. Despite the technological progress, 2025 was a year of near death for Wolfspeed. The company had taken on enormous debt, peaking at around $6.5 billion to fund its construction projects. This debt was predicated on aggressive growth forecasts for the EV market. When that growth slowed, Wolfspeed was caught in a perfect storm: high interest rates, massive capital expenditures, and delayed revenue. On June 30, 2025, Wolfspeed filed for Chapter 11 bankruptcy protection. In the corporate world, bankruptcy often signals the end. For Wolfspeed, it was a strategic reset. The filing was pre-packaged, meaning the company had already negotiated the terms with its major creditors before walking into court. They had the support of 97% of their senior note holders and their key customer, Renesas Electronics. The speed of the restructuring was unprecedented. Wolfspeed emerged from Chapter 11 on September 29, 2025, just 91 days later. The result was a transformed balance sheet. The process eliminated approximately $4.6 billion in debt, reducing the total burden by roughly 70% and cutting annual interest payments by 60%. This was a painful process for shareholders, whose equity was severely diluted, but it saved the company's operations. The factories kept running, the workers kept building, and the customers kept receiving chips throughout the entire 91-day period. As part of this new era, Wolfspeed made a difficult decision to sever ties with its past. The company announced the permanent closure of its legacy 150mm manufacturing facility in Durham, North Carolina by late 2025. This facility, which had birthed the silicon carbide industry, was simply too inefficient compared to the new 200mm plants. The closure resulted in a workforce reduction of approximately 20%, a necessary pruning to ensure the health of the larger organism. The future was solely in 200mm, and there was no room for nostalgia. The Wolfspeed story is ultimately a story of public-private partnership. The federal government decided that Wolfspeed was too strategic to fail. While the bankruptcy court handled the commercial debt, the IRS provided the cash flow to keep the lights on. In December 2025, Wolfspeed received a staggering $698.6 million tax refund from the IRS. This was part of the Section 48D Advanced Manufacturing Investment Credit, a provision of the CHIPS Act that allows companies to claim a 25% refund on their factory construction costs. Unlike a loan, this was cash, non-dilutive, immediate liquidity. Combined with the debt restructuring, this gave Wolfspeed a war chest of nearly $1.5 billion to finish its projects. This refund underscores the immense power of industrial policy. The government effectively paid for a quarter of the factory, ensuring that despite market volatility, the United States would retain its leadership in next-generation power electronics. While Wolfspeed swung for the fences with massive greenfield construction projects, its rival onsemi, formerly ON Semiconductor, headquartered in Scottsdale, Arizona, played a different game. Under the leadership of CEO Hassan El-Khoury, onsemi adopted a strategy called Fab Right. The philosophy was simple: don't build what you can buy and don't own what you can't optimize. Instead of spending 5 years building a new factory from scratch, greenfield, onsemi focused on buying existing older factories, brownfield, and upgrading them with modern technology. This approach is capital efficient, faster, and preserves existing skilled workforces. The centerpiece of onsemi's U.S. strategy is a massive facility in East Fishkill, New York. This site is hallowed ground in the semiconductor industry. It was built by IBM in the early 2000s as one of the world's most advanced chip factories. It was later sold to GlobalFoundries, a contract manufacturer. In a complex deal finalized in early 2023, onsemi acquired the East Fishkill facility from GlobalFoundries for $430 million. For a factory of this size, capable of running 300mm or 12-inch wafers, this price was a bargain. The logic was strategic. GlobalFoundries was using the plant to make logic chips, CPUs, processors, but was moving that production to other sites. onsemi needed a large U.S. facility to make power discretes and ultra-sensitive image sensors for cars. By buying EFK, onsemi secured the only 12-inch fab in the U.S. capable of manufacturing these specific power technologies. The transition of the factory was a feat of engineering. onsemi had to convert a plant designed for logic chips to one capable of producing high-voltage power transistors and ultra-sensitive image sensors for cars. This involved installing new tools and retraining the workforce. Crucially, the acquisition saved over 1,000 high-tech jobs in the Hudson Valley that might otherwise have been lost as GlobalFoundries exited the site. By 2025, the plant had become the workhorse of onsemi's U.S. operations. In the second quarter of 2025 alone, onsemi shipped over 5 million units of products manufactured on its new Trio platform from the East Fishkill fab. The Trio platform is a prime example of onsemi's technical innovation. It is a manufacturing process that allows for the creation of highly integrated analog and power chips on 65nm nodes. By running these on large 300mm wafers at East Fishkill, onsemi achieves a cost structure that competitors using smaller wafers cannot match. This allows them to offer premium products at competitive prices, driving the gross margin expansion that Wall Street craves. onsemi's strategy is not isolationist. While investing in New York, the company simultaneously launched a massive expansion in Europe. In 2024, onsemi selected its existing site in Rožnov pod Radhoštěm, Czech Republic, for a vertical silicon carbide expansion. This project, supported by a $450 million grant approved by the European Commission, is worth nearly $2 billion. It is designed to be an end-to-end facility, handling everything from growing the crystal to packaging the final chip. Why build in Europe when you have a massive fab in New York? The answer is supply chain resilience. onsemi aims to serve European automakers like Volkswagen and BMW from Europe and American automakers from the US. This local-for-local strategy insulates the company from shipping disruptions and trade wars. It allows onsemi to hedge its bets, leveraging subsidies from both the US CHIPS Act and the European CHIPS Act to fund its growth. While automotive has been the traditional driver for power chips, 2025 saw the emergence of a new, voracious consumer of energy: artificial intelligence. AI data centers are essentially massive heaters. They consume gigawatts of electricity to train models. The efficiency of the power supply units, or PSUs, in these server racks has become a critical bottleneck. Recognizing this, onsemi went on a targeted acquisition spree to build what it calls the complete power tree for data centers, controlling every step of power delivery from the building's grid connection down to the processor core. In January 2025, onsemi acquired the silicon carbide JFET business from Qorvo. This specific type of transistor is exceptionally good at circuit protection and high-efficiency switching, making it ideal for the power supplies in AI servers. Later in the year, onsemi acquired Vcore Power Technologies from Aura Semiconductor. This gave them the intellectual property for the controllers that manage power delivery directly to the GPU. By combining these acquired technologies with their manufacturing muscle in East Fishkill, onsemi positioned itself as a critical supplier to the AI boom, diversifying away from a pure reliance on electric vehicles. The Fab-Right strategy is efficient, but efficiency can be painful. To optimize its global footprint, onsemi had to make difficult cuts. In February 2025, the company announced a restructuring plan that involved reducing its global workforce by approximately 2,400 employees. These cuts were focused on exiting legacy products and closing older, inefficient factories that did not fit the new high-tech model. It highlights the dichotomy of the modern semiconductor industry. While the sector is growing and hiring aggressively for new technologies, like in East Fishkill and the Czech Republic, it is simultaneously shedding jobs in older, commoditized areas. The net result is a workforce that is smaller but more highly skilled and productive. Polar Semiconductor. If Wolfspeed is the high-risk pioneer and onsemi is the pragmatic giant, Polar Semiconductor is the quiet strategist. Located in Bloomington, Minnesota, Polar operates as a merchant foundry. Unlike Wolfspeed and onsemi, which design and build their own chips, integrated device manufacturers, or IDMs, a merchant foundry builds chips designed by other companies. Polar's story in 2024-2025 is a masterclass in how federal policy can fundamentally alter corporate structure to serve national security interests. For years, Polar Semiconductor was majority-owned by Sanken Electric, a Japanese company, with a minority stake held by Allegro Microsystems. While Polar operated in the U.S., its ultimate control resided overseas. The CHIPS Act changed the calculus. A core goal of the legislation is to ensure that the U.S. has domestic control over the supply of chips used in critical infrastructure and defense. Polar produces high-voltage sensors and power chips that are vital for aerospace, defense systems, and the power grid. To unlock federal funding, a transformative deal was struck. Niobrara Capital and Prism Capital, two U.S.-based private equity firms, agreed to invest $175 million to buy out the majority stake in Polar. This deal effectively transferred control of the company from Japan to the United States. Sanken and Allegro remained as minority investors and customers, but the governance flipped to the U.S. This re-domestication was a prerequisite for the government support. In September 2024, the Department of Commerce finalized a $123 million direct funding award to Polar, the first commercial manufacturing award to be finalized under the CHIPS program. This was a clear signal. The U.S. government is willing to pay to repatriate corporate control of critical technology. With the ownership issue resolved and federal funding secured, Polar launched a massive $525 million expansion of its Bloomington facility. This facility, which traces its roots back to the 1960s era of Control Data Corporation, was in dire need of modernization. The project aims to double the production capacity from approximately 20,000 wafers per month to nearly 40,000 wafers per month. But it is not just about volume, it is about capability. The investment funds new automation systems and AI-driven manufacturing tools that allow the fab to produce more complex, higher-voltage chips with better yields. The state of Minnesota contributed $75 million from its Minnesota Forward Fund, recognizing that this expansion would create 160 high-quality jobs and anchor the state's tech ecosystem for another generation. As a medium-sized foundry, Polar cannot compete on scale with giants like TSMC. Instead, it competes on specialization and partnership. In December 2025, Polar announced a strategic collaboration with UMC, Unimicro Electronics Corporation, one of the world's largest foundries based in Taiwan. Under this agreement, UMC will direct some of its customers to manufacture their chips at Polar's Minnesota fab. This allows UMC to offer Made in USA options to its clients without building its own US factory, while filling Polar's expanded capacity. Additionally, Polar signed a technology licensing agreement with Tower Semiconductor to utilize Tower's 180-nanometer process technology. This specific technology is highly valued in the defense sector for its reliability and power management capabilities. By licensing it, Polar can manufacture these specialized chips domestically, further cementing its role as a trusted supplier to the U.S. military-industrial complex. Defense and Foundry Services. In 1990, the United States was responsible for 37% of the world's semiconductor manufacturing capacity. By 2022, that figure had withered to just 12%. The implications of this shift are profound. Modern warfare is an electronic endeavor. A single modern fighter jet processes more data in a single mission than entire air fleets did during the Vietnam War. The efficacy of these systems relies on trusted electronics, components guaranteed to be free of malicious Trojan horses or kill switches that could be activated by an adversary. When production is offshore, maintaining this chain of custody becomes an insurmountable challenge. The risk of intellectual property theft, counterfeiting, and supply chain interdiction increases exponentially. A smartphone is obsolete in 3 years. An aircraft carrier or a B-52 bomber serves for decades. The F-35 is expected to fly until 2070. Consequently, the military requires a guaranteed supply of mature node chips, examples 90 nanometers, 130 nanometers, long after the commercial world has deemed them antiques. These chips are not inferior. In many high-power or high-radiation environments, older, larger transistor geometries are physically superior to fragile nanoscale components. The CHIPS Act recognizes this divergence, allocating specific funding not just for the leading edge, but for the sustained edge that keeps the military operational. Skywater Technology. Skywater Technology, headquartered in Bloomington, Minnesota, stands as a unique entity in the semiconductor landscape. It is the only US-owned and US-operated pure-play foundry that specializes in technology as a service, TaaS. Traditional foundries, like Taiwan's TSMC, operate on a volume model. A customer sends a design file, and the foundry prints millions of identical copies using a standard recipe. Skywater flips this model. They invite customers, often defense contractors or deep tech startups, into the lab to co-develop the manufacturing process itself. This is critical for defense applications, where the secret sauce is often not just the design of the chip, but the exotic materials or unique layering techniques used to build it. The Bloomington facility itself is a testament to the resilience of American tech. Originally built in the 1980s by Control Data Corporation, a pioneer in supercomputing, it was later acquired by Cypress Semiconductor before being spun out as an independent U.S. foundry. This lineage means the facility is deeply rooted in the ecosystem, with a workforce that spans generations. In December 2024, the Department of Commerce announced a preliminary Memorandum of Terms, PMT, to award Skywater up to $16 million in direct funding. While this figure appears modest compared to the billions grabbed by Intel, its strategic leverage is immense. This federal grant is unlocked alongside $19 million from the state of Minnesota's Forward Fund, a state-level instrument designed to match federal investments. When combined with private capital, the total investment in the Bloomington site is projected to exceed $350 million over the next few years. The funding is specifically earmarked to modernize the production of 90 nanometer and 130 nanometer wafers, increasing capacity by approximately 30%. Why invest in 90 nanometer technology in the 2020s? Readout Integrated Circuits, or ROICs. These are the unsung heroes of modern vision systems. An ROIC sits directly behind the sensor array in a thermal imaging camera or night vision goggle. It processes the raw electrical signals from each pixel into a coherent image. Skywater's expansion directly bolsters the supply of these chips for the U.S. Army's thermal weapons sights and enhanced night vision goggles. Radiation hardening, or rad-hard. Electronics in space are bombarded by high-energy protons and heavy ions that can flip bits, changing a 0 to a 1, or permanently burn out circuits. Skywater creates rad-hard chips using specialized insulating layers and circuit designs that are immune to this cosmic interference. This capability is non-negotiable for the U.S. Space Force and nuclear deterrent systems. Superconducting and photonics. The TAS model allows Skywater to experiment with superconducting ICs for quantum computing and photonics for high-speed data transfer, technologies that are on the bleeding edge of future defense capabilities. The story of Skywater is not without its setbacks, and the cancellation of its planned facility in Indiana serves as a critical case study in the limitations of the CHIPS Act. In July 2022, Skywater announced plans to build a $1.8 billion semiconductor R&D and fabrication facility in the Discovery Park District at Purdue University in West Lafayette, Indiana. The announcement was met with jubilation. It promised 750 high-tech jobs and seemed to anchor the idea of a Silicon heartland. The logic was sound. Purdue University possesses one of the finest engineering programs in the country, providing a ready-made pipeline of talent. However, by early 2024, the project was effectively dead. Skywater released its option on the land, and the plans were shelved. Why did it fail? The project was heavily predicated on receiving a massive injection of CHIPS Act funding. Skywater, as a mid-sized company, revenue around $286 million in 2023, could not finance a $1.8 billion greenfield project on its own balance sheet. When the Department of Commerce began prioritizing the modernization of existing, proven facilities like Bloomington and the massive leading-edge projects like Intel in Ohio, the math for the West Lafayette project collapsed. The federal funds simply weren't there in the quantity required to make the risk acceptable. The resilience of the Indiana ecosystem, however, was proven in the aftermath. Just as the Skywater deal disintegrated, the state secured a massive $3.87 billion investment from SK Hynix, a South Korean giant, to build an advanced packaging facility in the same research park. This illustrates a key dynamic. While individual corporate projects may fail due to specific financial constraints, the aggregated value of regional tech hubs anchored by research universities like Purdue remains a powerful draw for capital. For Skywater, the retreat allows them to consolidate resources into the sure bet, their thriving, funded, and expanding facility in Minnesota, BAE Systems. If Skywater represents the open foundry model, BAE Systems represents the captive defense facility, a factory that builds chips solely for the purpose of putting them into the company's own weapons systems. The Microelectronics Center, MEC, in Nashua, New Hampshire, is a cathedral of defense technology. Spanning 110,000 square feet, it is an accredited DoD-trusted foundry, with a lineage tracing back to Sanders Associates, a legendary defense electronics firm from the 1950s. It is highly significant that BAE Systems received the very first grant announced under the CHIPS Act, $35.5 million awarded in December 2023. This was a statement of intent by the Biden-Harris administration. National security is the primary directive. The Nashua facility does not produce the silicon logic chips found in computers. It specializes in monolithic microwave integrated circuits, MMICs. These are chips designed to manipulate the electromagnetic spectrum, radio waves, and microwaves. To understand the importance of this, one must understand the difference between silicon and compound semiconductors, like gallium arsenide, GaAs, and gallium nitride, GaN. Silicon is excellent for logic, processing information. Gallium nitride is the champion of power and frequency. Electrons move through gallium much faster than through silicon, and the material can withstand much higher voltages and temperatures. For a fighter pilot, gallium is the difference between life and death. A radar built with gallium chips can broadcast a more powerful beam, detecting enemy aircraft at greater ranges. Conversely, a gallium-based jammer can pump out enough radio frequency energy to blind an enemy radar from a safer distance. BAE Systems is one of the few domestic foundries capable of producing 6-inch gallium and gallium arsenide wafers specifically tuned for these military applications. The crown jewel of BAE's portfolio is the ANSQ-239 Electronic Warfare (EW) suite for the F-35 Lightning II. The F-35 is often called a stealth fighter, but its stealth is not just about its shape, it is about its ability to manage its electronic signature. The ANSQ-239 system, powered by the MMICs made in Nashua, provides the pilot with 360-degree spectral awareness. It passively listens for enemy radar signals. When a threat is detected, say a Russian S-400 surface-to-air missile battery tracking the jet, the system identifies the frequency and location. It can then direct the F-35's own radar to jam the signal or deploy decoys. The modernization funded by the CHIPS Act is directly linked to the Block 4 upgrade of the F-35. This update is designed to counter emerging threats from peer adversaries, China and Russia. The new MMICs will enable the F-35 to detect more agile frequency-hopping radars and engage well-defended targets in signal-dense environments. The $35.5 million grant will replace aging tools in the fab, quadrupling the production capacity for these chips and cutting the modernization timeline in half, ensuring that the supply of EW modules keeps pace with the production of the aircraft. A semiconductor fab is useless without the hands to run it. BAE Systems faces a demographic cliff. Many of the expert technicians who have run the Nashua fab for decades are nearing retirement. The CHIPS Act funding includes a mandate for workforce development, which BAE has addressed through a partnership with Nashua Community College. The Microelectronics Bootcamp is a 10-week intensive course designed to take individuals with zero semiconductor experience and turn them into certified operators. The curriculum covers wire bonding, die attach, and inspection, the manual dexterity skills required to assemble military-grade chips. The social impact of this program is profound. Snippets revealed that at least 75 students who graduated from the program identified as homeless prior to enrollment. The program, supported by community agencies, provided them with a pathway to stable, high-paying jobs at BAE Systems, achieving a 97% hiring rate. This integration of social policy, homelessness reduction, with industrial policy, chip manufacturing, represents the holistic approach of the CHIPS Act implementation. Rogue Valley Microdevices. If Skywater and BAE are the established powers, Rogue Valley Microdevices, RVM, is the insurgent. The company's origin story is the stuff of Silicon Valley lore transposed to the forests of Oregon. In 2003, Jessica Gomez and her husband, Patrick Kayata, founded RVM. They were not wealthy venture capitalists. Gomez was 26 years old, holding a 2-year degree from a community college and working in the industry. When a previous employer went defunct, they saw an opportunity to buy the used equipment, scavenging the innards of a clean room that would otherwise have been scrapped. To finance the startup, they sold their home in California, using the $180,000 in equity as their seed capital. They maxed out credit cards to cover the rest, starting with roughly $50,000 in debt. The early days were brutal. The fab lacked air conditioning for the first 2 years because they couldn't afford a chiller system. They did everything themselves, from sales to running the furnaces. The 2008 financial crisis nearly wiped them out. They were forced to lay off their entire staff and reboot the company from scratch. But they survived, pivoting their business model and slowly rebuilding. Today, RVM is the first woman-owned and minority-owned business to receive CHIPS Act funding. Rogue Valley specializes in micro-electromechanical systems, MEMS. Unlike the logic chips made by Intel, which simply process information, MEMS chips interact with the physical world. They contain tiny moving parts, gears, mirrors, vibrating beams, carved out of silicon. Why are MEMS critical for defense? Inertial navigation. MEMS accelerometers and gyroscopes form the inertial measurement units, IMUs, used in missiles, drones, and aircraft. If a GPS signal is jammed by an adversary, a common tactic in modern electronic warfare, the MEMS IMU takes over, allowing the weapon to navigate by dead reckoning. Biosensing. MEMS microfluidic devices can detect trace amounts of biological or chemical agents. During the COVID-19 pandemic, RVM pivoted to manufacturing MEMS for rapid testing devices, showcasing the dual-use nature of the technology. Optical switching. MEMS mirrors are used in optical networks and laser steering systems for LiDAR and directed energy weapons. In July 2024, the Department of Commerce awarded RVM up to $6.7 million in direct funding. While a fraction of the BAE award, this money is transformative for a company of RVM's size, $10 million annual revenue. It supports the construction of a new fab in Palm Bay, Florida, on the Space Coast. The technological ambition here is significant. RVM plans to be the first MEMS foundry in the world to offer 300mm wafer capability. Most MEMS are made on small 150 or 200mm wafers, 6 or 8 inches. Moving to 300mm, 12 inches, is a massive leap. It allows for huge economies of scale, producing more chips per batch. Crucially, standard advanced logic chips, processors, are made on 300mm wafers. By matching this size, RVM can more easily integrate its MEMS sensors directly onto the same wafers as the processor, creating smart sensors with zero latency. This expansion will triple RVM's capacity and place it physically closer to the aerospace giants NASA, SpaceX, and L3Harris operating in Florida, tightening the feedback loop between design and manufacturing. Advanced packaging and substrates. For decades, the industry was guided by Moore's Law, the observation that the number of transistors on a microchip doubles approximately every 2 years, leading to exponential increases in performance and decreases in cost. This singular focus on shrinking the transistor drove the industry to create features measured in angstroms, tenths of a nanometer. However, as we enter the angstrom era, traditional 2D scaling is hitting hard physical and economic walls. Shrinking transistors further is becoming exponentially more expensive and yielding diminishing returns in power efficiency. The industry's response is advanced packaging. If traditional manufacturing is like building a sprawling single-story city, advanced packaging is the construction of a high-density vertical metropolis. By stacking chips on top of one another or arranging them side by side on ultra-fast interposers, engineers can achieve higher performance and lower power consumption without needing to shrink the transistor further. SK Hynix. SK Hynix, a South Korean semiconductor titan, has chosen West Lafayette, Indiana, as the site for a transformative investment that redefines the technological capability of the American Midwest. The company is establishing an advanced packaging fabrication and R&D facility with an expected capital expenditure of approximately $3.87 billion. The West Lafayette facility focuses on high-bandwidth memory, HBM, a specialized type of dynamic random access memory, DRAM, that is essential for AI. Unlike standard memory, which lays flat on a circuit board, HBM consists of vertically stacked DRAM dies connected by microscopic vertical tunnels called through-silicon vias, TSVs. This vertical architecture allows for massive data throughput. The next-generation chips produced at this facility will process up to 1.18 terabytes of data per second, equivalent to transferring 230 full HD movies in a single second. AI training involves performing trillions of calculations on massive datasets. If the memory cannot feed data to the GPU fast enough, the processor sits idle. HBM solves this memory wall problem. The U.S. Department of Commerce has awarded SK Hynix up to $458 million in direct funding, recognizing that HBM production is a national security imperative. Currently, HBM production is concentrated in Asia. By bringing this capability to Indiana, the U.S. secures a domestic source for the critical fuel of AI systems. The location at the Purdue University Research Park is deliberate. It facilitates a deep integration with the Burke Nanotechnology Center for R&D on heterogeneous integration and memory-centric architectures. This is not merely a production line, it is a research hub designed to keep the U.S. at the forefront of memory technology. The project creates approximately 1,000 new jobs. To fill these roles, SK Hynix is partnering with Purdue, Ivy Tech Community College, and Indiana State University to develop specialized curricula. Environmentally, the facility aims to run on 100% carbon-free electricity by the early 2030s and implement advanced water conservation strategies, a crucial factor given the water-intensive nature of semiconductor manufacturing. Amkor Technology. While SK Hynix focuses on the memory component, Amkor Technology provides the broader architecture that ties these components together. Amkor is constructing a $2 billion advanced packaging and test facility in Peoria, Arizona. Amkor is an outsourced semiconductor assembly and test provider. In the modern ecosystem, companies like NVIDIA design chips and foundries like TSMC fabricate the silicon wafers. However, those wafers are useless until they are cut, packaged, and tested. This is the role of the OSAT. The Arizona facility will specialize in 2.5D packaging. In this configuration, logic chips like GPUs and memory stacks like HBM are placed side by side on a silicon interposer. This interposer acts as a high-density bridge, allowing the chips to communicate with extremely low latency. The facility's location in Arizona is strategic, placing it in close proximity to TSMC's massive new fabs. This allows for a wafer-level handoff, where wafers produced by TSMC can be immediately transported to Amkor for packaging, significantly reducing logistics risks and cycle time. Supported by up to $400 million in CHIPS Act funding and $200 million in loans, the project is expected to create 2,000 jobs. A key differentiator of the OSAT sector is the accessibility of its jobs. Unlike chip design, which requires advanced degrees, many advanced packaging roles require technical certifications that can be obtained through community college programs, offering robust economic opportunities for the local workforce without requiring four-year degrees. Absolics. Beneath the silicon chips and the interposers lies the substrate, the physical platform that connects the package to the rest of the computer. For decades, substrates have been made of organic plastic laminates. However, the heat and density of modern AI chips are pushing organic materials to their breaking point. In Covington, Georgia, Absolics, a subsidiary of SKC, is pioneering the commercialization of glass substrates, a technology that promises to overcome the limitations of organic materials. Supported by up to $75 million in direct CHIPS funding, Absolics is building a 120,000 square foot facility to mass produce this breakthrough material. The shift from organic to glass is analogous to the shift from vacuum tubes to transistors. It changes the fundamental capabilities of the device. Glass is incredibly flat and stiff. This allows for finer lithography, meaning wires can be etched closer together, finer pitch. This density allows for more data channels between chips. Organic substrates tend to warp when exposed to the high heat of reflow ovens during manufacturing. Glass remains rigid. This stability is critical for large multi-chip packages used in AI servers. Glass has superior electrical properties that reduce signal loss, leading to lower power consumption for the final device. The technology behind Absolics was developed in collaboration with the Georgia Institute of Technology, showcasing a successful transfer of academic research to commercial manufacturing. The importance of this technology was further validated when Absolics was selected to receive up to $100 million in R&D grants from the National Advanced Packaging Manufacturing Program, NAMP. This designates the Georgia facility as a global epicenter for next-generation packaging materials. The project is expected to support 1,200 jobs, including construction and high-tech manufacturing roles. Absolics is investing heavily in the local community, committing over $100,000 annually to workforce development and partnering with Georgia Piedmont Technical College to train the local labor force. Supply chain, equipment and materials. As chip manufacturing becomes more complex, the cost of R&D has skyrocketed. No single company can afford to develop every tool and process in isolation. The industry is moving toward a collaborative model, spearheaded by the largest equipment manufacturer in the world. Applied Materials is investing up to $4 billion to build the Equipment and Process Innovation and Commercialization Center in Sunnyvale, California. This facility is designed to be the Switzerland of the semiconductor industry, a neutral ground where rivals and partners can collaborate to solve physics-level problems. Currently, there is a significant lag between a university breakthrough and its implementation in a high-volume fab. It can take years to transfer a process from a research lab to a commercial tool. The EPIC Center provides over 180,000 square feet of clean room space, where chip makers like Intel, TSMC, and Samsung can have their own dedicated zones within the equipment factory. By allowing chip makers to test new tools on-site, Applied Materials aims to shave years off the development timeline. This concurrent engineering model allows the tool and the chip to be designed simultaneously. The center will focus on the challenges of the Angstrom era, such as atomic layer deposition and etching. Furthermore, Applied Materials has been awarded $100 million from the NAPMP to develop silicon core substrates, a technology complementary to the glass substrates of Absolics, further diversifying the U.S. approach to advanced packaging. This investment anchors the R&D brain trust of the industry in Silicon Valley, creating up to 2,000 engineering jobs and ensuring that while manufacturing may expand globally, the invention of the technology remains in the U.S. Entegris. Behind the high-profile fabs and packaging plants exists a vast, invisible network of suppliers providing the picks and shovels of the digital age. These companies handle the extreme chemistry and physics required to manipulate matter at the atomic scale. Entegris is investing approximately $600 million to build a manufacturing center of excellence in Colorado Springs, Colorado. This facility is critical for ensuring that the intricate chips produced in fabs actually work. A central product of this facility is the front-opening unified pod, or FOUP. To the uninitiated, a FOUP looks like a plastic crate. In reality, it is a hermetically sealed, highly engineered microenvironment. A single 300mm wafer can hold hundreds of high-value chips. As these wafers travel miles on automated tracks inside a fab, even a single microscopic dust particle or a stray molecule of gas can destroy the circuitry. The FOUP creates a localized cleanroom environment for the wafers. Currently, FOUP production is concentrated in Asia. Entegris is reshoring this capability to Colorado, ensuring that U.S. fabs have a secure domestic supply of these critical transport vessels. The facility will also produce advanced liquid filtration systems. Modern chip manufacturing uses hundreds of specialized chemicals. If these chemicals contain impurities measured in parts per billion, the yield of the fab crashes. Entegris filters are the kidneys of the fab, constantly purifying the fluids to ensure manufacturing success. The project is supported by up to $77 million in CHIPS funding and will create approximately 600 jobs. Edwards Vacuum. Semiconductor manufacturing cannot occur in air. It requires a vacuum. Edwards Vacuum is establishing a $319 million dry pump manufacturing facility in Genesee County, New York, to support this need. In chip manufacturing, gases are introduced into a chamber to etch patterns or deposit layers on silicon. These gases must be evacuated precisely. Unlike industrial pumps that use oil for lubrication, semiconductor pumps must be dry or oil-free to prevent contaminating the cleanroom with oil mist. They also must be rugged enough to handle the corrosive and toxic gases pumped out of the chamber. There is currently no domestic production of semiconductor-grade dry vacuum pumps in the U.S. This investment fills a glaring gap in the supply chain, providing pumps to the nearby Micron and GlobalFoundries fabs. The location at the Science and Technology Advanced Manufacturing Park, or STAMP, utilizes New York's abundant hydropower. Edwards has committed to running the facility on 100% carbon-free electricity. The project, supported by up to $18 million in CHIPS funding, will create approximately 600 jobs and serves as a cornerstone of the NY Smart I Corridor, a tech hub connecting Buffalo, Rochester, and Syracuse. Hemlock Semiconductor. At the absolute beginning of the supply chain is sand, silica. Turning that sand into the ultra-pure silicon required for chips is the job of Hemlock Semiconductor in Michigan. HSC is the only U.S.-headquartered manufacturer of hyper-pure polysilicon. HSC is investing $375 million to expand its capacity, supported by a finalized CHIPS award of up to $325 million. While solar panels use polysilicon, semiconductor-grade polysilicon requires exponentially higher purity, often described as 11 nines, or 99.99999999999% pure. Impurities are measured in parts per trillion. Without this material, no wafer can be grown, and no chip can be built. HSC secures the base of the pyramid for the U.S. industry, ensuring that the raw material for the digital economy is not held hostage by foreign supply chains. The United States is executing a comprehensive, multi-layered strategy to reshore the semiconductor supply chain. This is not a scattershot approach. It is a deliberate architectural redesign of the industry. The U.S. ensures that the inputs are safe, the manufacturing infrastructure is robust, the pace of innovation accelerates, and the advanced packaging capabilities necessary to build the AI systems of the future are established. Also, by securing the domestic production of thermal imaging chips, electronic warfare jammers, and inertial navigation sensors, the United States is slowly rebuilding its silicon shield. This is a defense posture that relies not just on the brilliance of American design, but on the resilience of American manufacturing. This ecosystem represents a move away from the fragmented, fragile supply chains of the past toward a resilient, integrated domestic network. While challenges remain, particularly in workforce readiness and execution speed, the investments analyzed here provide the structural foundation for American technological leadership in the Angstrom era.